Awesome. Okay, so what's going to happen is we are going to get started with trees. Firstly, when we talk about trees, you're going to have to know what we're talking about in terms of graphs as well. So I'm just going to quickly go over what graphs are, just in a simple way. So say I have some nodes here. I'm just going to go through some of the terminology that we're going to be using today. And these nodes can have values. So this is a node, that's a value, and then this over here is an edge. So a node is just something in memory that has a reference to this value, and the edge is just a connector between two nodes. Okay, hopefully that's pretty easy to understand. Um, and then we're just going to move on. So, in terms of what a tree is a graph of nodes with a recursive structure and it has a root node. I'll also be giving out the notes in the chat after the lecture as well. So what we mean by this is, obviously, we talk about the graph of nodes. Recursive structure. Now, what a recursive structure is something that will repeat. So, for example, I'm just going to draw a tree, and you'll see what I mean. I'm not going to define the values since they don't really matter here. So, as you can see, we have this sort of structure in each of these different parts. That's what we mean by a recursive structure. It will repeat each time. Okay, and it has a root node. It doesn't have root nodes. It has a singular root node. And if I just go back to this implementation that we had here, this would be the root node. So what the root node is just a pointer to the main node inside of the tree. Okay, hopefully that all makes sense. Obviously, if you do have any questions, just pop them in the chat. But yeah, hopefully that's all good for now. Just let me know if there's anything that you don't understand, and I'll be happy to go through it as well. Actually, I'll leave this here. Okay. And then we also need to know some other terminology as well. So for this tree, we know that it has a root node, it has some internal nodes. And what we mean by internal nodes are nodes that are not the root. So I'll just write this down. Not root nodes. And also, they aren't what we call leaf nodes. Just explain that in a moment. So these leaf nodes over here are just a way of describing the nodes at the end of the tree. So this is just the nodes at the last layer of the tree. So we can have the first layer, the second layer. I'll just make it better. So we have these different layers. We know that 3 is the last layer, and so to refer to the nodes in this last layer, we just call them a leaf node. So this is a leaf node, this is a leaf node, that's a leaf node, that's a leaf node. That would be an internal node, and this as well. And then, like I said before, that's the root node. Okay, and that's just the basic terminology of trees. So we basically just covered most of the trees concepts, so that's good. And I'm just going to leave this here. Next, we're going to be talking about binary trees. So this is just a bit more Oh, it's a lesser generalization of what we were just doing before, because binary trees are trees with a bi, so that means they can have two nodes. They are binary trees. Now, I'm just going to break it up for you guys as well, just to sort of show what's going on. Um, so obviously, bi obviously means two. Nary describes the arity of that tree. So, for example, I could say that we have a tree of n array. So we can have an n-ary tree where n would be the number of nodes that are children. So what that means is, for example, when we talk about binary trees, if I just make a quick binary tree right here, so we've made a quick binary tree. Um, n-ary would be the number of nodes that are the children. So the children are just the nodes that connect from a specific root node or a specific node, for example. So let's take an example as the root node. The children would be the ones connecting from that specific singular node. So this is a child of that node. I'll just write it on the side. And then this is also a child of the root node. Hopefully that makes sense as well. So it's just another terminology that we use to refer to the nodes. So yeah, that's essentially what an n-ary tree is. Essentially, when you have n, which is a variable number, that just means that this n could be one, two, three, whatever you want it to be. Here, like I said, we're talking about binary trees. So that's two children. So it's not just two children though. You can have zero children in a node. You can have one children in a node. You can have two children in a node. It's not limited by that sort of n. N is just for max. So you can't have three nodes in a binary tree. Otherwise, that wouldn't make sense. So yeah, that's fine. So we're going to move on to binary trees then. Um, in terms of binary trees, there's a lot of different types of binary trees that I'm going to be going over as well. But let's take this binary tree. I'm just going to copy it over. Copy that. Put it over here. And I'm just going to do this several times because obviously there's going to be different types of trees that we need to know. So if you guys just give me a second, should be enough. So we're going to be starting off. What we are going to be doing is we're going to be talking about the different trees. So I'm going to be starting off by talking about complete binary trees. So these, yet again, is just a theory, and it's just a way of referring to specific types of binary trees. So I'll talk about a complete binary tree then. Actually, what I'll do is I'll just give it so that there's more space for writing explanations. Yeah. Okay, so complete binary tree. So what a complete binary tree is, is a tree where we have um, a nearly perfect tree. So, for example, something similar to this, but that last node isn't there. So I've just removed that node. So for this complete binary tree, um, we would know that there's uh, sort of k minus one nodes in the leaf layer. Remember, the leaf layer would be this layer over here. And what we mean by k minus one is, if we look at this specific tree, for example, if I label these with zero-based indexing, so that just means that we're starting the indexing from zero. We have 0, 1, and 2. And what you'll see is that if we do 2 to the power 0, 2 to the power 1, and 2 to the power 2, we actually get the size, or the maximum size of each full layer of the binary tree. Because obviously 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4. And you can see that we've got one node here, we've got two nodes here, we've got three nodes in this specific binary tree. But like I said, this is a formula for the full layer, or the maximum amount of nodes in a tree. So we'll just put 2 to the power n is equal to a maximum amount of nodes in the tree. Is that making sense as well, guys? Just like drop a yes in the chat. Yeah, perfect. So, okay. And then referring back to k minus 1 then, so like we've said, we have this over here. What I'll do is I'll just remove this. We'll just refer to that leaf layer, like I said. So 2 to the power 2 minus 1 is equal to 3. So that's what we mean by k minus 1, where k is the size of, or the number of nodes in the leaf layer. So that's a complete binary tree. It just means that there's k minus 1 nodes in the leaf. Okay? Next, we're going to be moving on to full binary trees. What I'm going to do is, yet again, I'm just going to move everything over just for space, just so it's easier. And we'll highlight this as well. So, full binary trees. Now, what a full binary tree is, it's pretty simple. All it is that any node can only have either 0 children, they can only have 2 children. So that's what it is. So for example, let's take this tree. This would technically be a full binary tree because each node has two children, and no node has one child. Um, but let's say if I did this, is that a full binary tree? Yes or no? Put it in the chat. Yeah, no, good. Yeah, so you're right, guys. So that's not a full binary tree. But if I were to do this, is that a full binary tree? Yeah, nice. So yeah, that's basically what a full binary tree is. So like we've said before, 0 or 2 children, and it seems like it's making sense. So I'll move on. The next type of binary tree that you need to know, what I'll do is I'll just do it here, um, is a perfect binary tree. Okay. Now, perfect binary trees are one are a type of tree where all the interior nodes or all the internal nodes have two children and all the leaf nodes are at the same level. So what this means is that all of these internal nodes, like we were saying, have two children, which here they do, and all the leaf nodes are on the same layer. So what this means is, I'll give you an example on this one. So technically this would be a perfect binary tree, but we can also have it such that if we remove this, that's also a perfect binary tree. But if we remove these two, this is no longer a binary tree. Because firstly, there's no two nodes for each node, and that's internal. Or if I just clarify no words, for all of the internal nodes, what we should have had is two children, but here there's none. I mean, here there's no two children. We only have one child per node, and hence it's not a perfect binary tree. Then we have that, but we can also have it such that if I put this node back, but I also do this, is that a perfect binary tree or not? Just let me know in the chat. Yeah, Manjeev, you're right. It is balanced, but it's not perfect. Yeah, but yeah, you're right, Shay. It would also be a complete binary tree as well. Um, so remember if we were going back to the complete binary tree. Oh wait, no, it's not complete, sorry. It's a full binary tree. Complete binary trees would have k minus 1 nodes in the leaf. So, all right. And then I can also see that pseudo alibi's got a question. Is balanced the same thing as perfect? So balanced isn't the same as perfect. And also k is the number of nodes, maximum number of nodes in the leaf layer. Okay. Isn't it complete when all the levels are completely filled except possibly the last? Just bear with me one sec. Okay. Okay, so yeah, no, wait. Yeah, you're right. So in this scenario, it's not actually k minus 1. Um, yeah, so yeah, that's fine. But if just draw this out one sec. So if I'm just gonna go back to the complete binary trees. We're also gonna go back to balanced trees and unbalanced trees as well. And I'll do that in a moment just to answer your question. But I'll just make everything clear. So okay. So complete binary trees. I actually got the definition wrong, so thank you for correcting me, Shane. So this means that every layer, I mean every uh, level except the last level. If I'm going to list as well, is 4. So, for example, in this specific case, it would still be a complete binary tree. Um, but although if I go back to this tree, obviously I had not added these 2 extra nodes over there. What you would see is that this isn't a complete binary tree though, because it's not just the last level, it's this level as well. So because we have 2 levels that are incomplete, that means that this isn't a complete binary tree. Hopefully that's making sense. Okay, and then we're gonna be moving on to pseudo alibis question in terms of balanced trees as well. So, and also if I am obviously going too fast, just let me know, or if there's any questions that you have, just let me know as well. Okay. So balanced versus unbalanced trees. Okay. So, like we were having a look at these trees before, if I just bring this tree here, I'm also just going to quickly make another tree as well. Okay. So we have a balanced tree on the left side and the unbalanced tree on the right side. And a balanced tree just means that it's not sort of heavy on one side and unheavy on the other. It just means that it's got a time complexity for a search where it is of log n. So if I just see if I can find anything in this, because, well, so what we mean by this is, firstly, say if we have some values, I'm just going to add some values in here. And remember, obviously, we're not talking about binary search trees just yet. So this is just a normal binary tree. So we don't need to have a look. So let's say we've just numbered the nodes here. These aren't um, sort of specific or anything. But let's say I wanted to find 7 in the tree. Um, and to be fair, now would actually be a good time to introduce binary search trees as well. So what I'll do is I'll actually renumber them. Just bear with me one moment. 25, 3, 4, 1, 6. No, I'm going to do 7, 6, and 8. Can you guys see that as well? Extra the balance out the given that is a difference in the balance between the left and the right sectors. The balance from 0 at every. Yeah, that's right. Yeah, perfect. Also, so yeah, like Hux is saying, if we have a balanced tree, that means that the number of nodes on each side is balanced in the children. Uh, and yeah, so like Shay's saying as well, it's perfectly balanced if it's 0, but when we talk about AVL trees as well, it's balanced if it's -1 or 1, but that's talking about AVL trees, which I'm also going to be doing a lecture on. I think it's next week as well, so we'll have to talk about that. That's something I'm going to be talking about as well. And Yeah, so here we have a binary search tree. And what I'm going to be doing is I'm going to talk about binary search trees first, and then move on to the balanced, because you do need to have some background knowledge regarding binary search trees. So binary search trees, you have binary search tree. So when we think about binary search, obviously we know that's a sorting algorithm. I mean, a searching algorithm, sorry. Um, it's a searching algorithm that runs in log of n time, or O of log n time. Now, what this means is that the upper bound of the time that it runs in, or the number of steps that it runs in with respect to n inputs, is log of n. And I'll just show you a quick example just to give you an idea. So let's say we have this array, right? I'm just going to quickly go through binary search and then we'll get back to trees as well. Um, so, for example, the way binary search works is we have a left pointer, we have a right pointer, and for each iteration, we are going to be calculating a middle. So obviously we know that arrays are zero-based indexed. So obviously everything starts from zero, right? So this is the index, this is the value, and here I'm just going to write the pointers. So obviously, to work out the middle, we need to do the left pointer plus the right pointer divided by 2. So that would be 7 plus 0 divided by 2, which is 3.5. Now, oh, is it lagging? Oh, it's back now. Okay, cool. Um, so yeah. So 3.5, obviously in code, we would not do this because when we define our code, firstly, arrays don't have decimal indexes. And also, integers do not contain decimals. So what the code does is it will do 7 plus 0 divided by 2, which is 7 divided by 2. But it will just divide 7 up until the point where there's no longer anything to divide. So that means this in code will return 3. So that means our middle is at index 3 right here. Okay. I'm just going to move everything just to a nicer place as well. So our index is at 3 for the middle. So let's say we're trying to find 8, target 8. And we wouldn't actually need to use the floor function um, here. That would just be a bit redundant, I would say. But you can still use it, which is fine. That's only if you're going to be using any sort of data type that supports, because integer division automatically rounds down. Yeah, basically. So it's like what I've explained here. It will divide until there's nothing to divide. So it will do, I'll just quickly go into depth a little bit. So 7 divided by 2. So 7, we have 2 times 2 times 2, which is equal to 6, right? And then we have 1, obviously 1 as the remainder. What the code does is it factors in these 3 2s. It doesn't care about that remainder, because obviously at that point we're doing 1 divided by 2. So yeah, you're right, Shay. So the floor is implicit. And by floor, what we mean is we're just rounding down. That's the whole point of the floor function. Okay. So let's go back to this then. So we have the middle at 3, and we're trying to find 8. Actually, what I'll do is draw a proper box around it. So we have 8 as the target, and we're at the middle here. Now, we know that 4 is an 8, but 4 is not bigger than 8 either. But 4 is less than 8. So essentially, because we know, obviously, in the binary search as well, that the array is sorted. So 1, 2, 3, 4, 5, 6, 7, 8. And by the way, binary search will not work on unsorted arrays as well. So we know that the array is sorted, which implies that everything that's behind that 4 in the array will be smaller than 4. So essentially, we don't really care about this anymore. We can just do this. And we don't need to consider it. And now the way that we ignore everything from 4 to 1 is we move this left pointer to the index of the middle plus 1, which is here. Because obviously the index of the middle is 3, plus 1 is 4. Then we do that same calculation again. We're at the second iteration. So I'll write the number of iterations here. Obviously, 4 plus 7, remember we're looking at the indexes to find the middle. 4 plus 7 is 11, divided by 2 is equal to 5.5, but obviously implicit flooring or implicit rounding down in integer division, so it's 5. So we look at the fifth index. This is our middle now. 6, like we said before with 4, smaller than 8. It's not 8, but it's not bigger than 8 either. So we don't care about 6 and what's before it. So we do an update of the left pointer, which is equal to m plus 1, or the middle plus 1. So L is here now, and we do not care about everything else that's here. And I'll just draw a partition here as well, just to emphasize. And then we're on our second iteration. That was our second iteration. Now we're on to our third iteration. We have 6 plus 7, which is equal to 13, divided by 2, which is equal to 6. Obviously, I have skipped that 6.5 part. So our middle is also here as well. So yet again, 7 is not 8, it's less than 8, it's not bigger than 8. So we move the pointer to m plus 1, which is here. So now R and L are actually both on the same thing. And that's where in the binary search we stop. That's the stopping condition. So when L is equal to R, when the pointer to one index at the left is equal to the pointer for the index at the right, we stop. And we will quickly check to see if this is the value. If it's not, then we continue and finish, and we say that obviously the value isn't there. And then actually, we can also have another stopping condition as well, which is this. And also, yeah, you're right, Shay. So when the middle is the target. Yeah, yeah, cool. So I'll just explain both again. So our first stopping condition is when the left pointer is greater than or equal to the right pointer. Here it's equal. And then when m is equal to the target, which just means that we found the target that we want. So, okay, so now we've stopped. We've checked, is this last pointer, is this 8? And it is actually 8. So we know that 8 is in the index at 7. And that's binary search in a nutshell. So now we found 8. That took us 3 iterations. So that was the first iteration here, second iteration here, third iteration here. And yes, Manjeev, this is for a search. So we're just searching in a sorted array. Yeah, that's it. And then, like we said, we have 3 iterations. Now, binary search works, like I said, we talked about it before, works in log n time, where the base is 2. So we can now prove this because n obviously is the input size. And if we do log 2 of 8, which is the input size, which is the length of the array, we get 3. It took us 3 iterations to find that. And that's the whole point of binary search and how it works. And then if we come back to binary search trees, it's basically the same thing. What we do is, in our binary search tree, we have a tree in which all the nodes are sorted. Yeah. So yeah, we are going to be coding this as well. We're going to be doing that once we've covered everything. I've got some examples as well. We're going to be coding up a binary search tree. So yeah. So a binary search tree, like we said, it's a sorted tree and it allows us to have log n time complexity for searching in a good case. We'll talk about good cases and bad cases in a bit, but I'll just quickly bring this back from here. So yeah, we have log n time complexity, and it's kind of similar to the array because thinking about it, let's say we're trying to find 8 again. So I'll write target is 8. The way we would do this is we have a look. Obviously, we start from the root node. So, and we say, okay, is 5 equal to 8? No, it's not. Is it bigger than 8? I mean, is the target bigger than 8? The target is bigger than 8, but is 5 bigger than 8? No, 5 is smaller than 8. So what we do is we move to the right because the point of the binary search tree, like I said, is sorted. So on the left side of the binary search tree, we have smaller items, but on the right side, we have bigger items or bigger values. So in order to find something that's bigger than 5, we move to the right. And let's move to this node. We'll move to the right hand of the root node. And in code, what we would do is, if we're at the root node, we would do root.right. Root.right is just a reference to the right node, which is this node over here. Okay? Hopefully that makes sense. Just let me know, obviously, if you have questions. So we're at the root. We're at the right node of the root, which is 7. And we just do the same thing again. We're looking for if we have a value in that node where it's smaller or bigger than 8. We're just going to compare it. So obviously 7 is not 8. It's not bigger than 8, but it's less than 8. And hence we move to the right again. And then we're now here. This is 8. So we know that 8 is in this tree. And then we can return true. Because obviously the whole point of a search was to see if something was in there. let's say if we tried to find target 9, now obviously at this stage we would be like 8 is not 9, 8 is less than 9, but it's not more than 9. So we move to the right. But we don't have a right. We don't have that right node. So that means that, because obviously here, if we had that left node here, that would be smaller than 8. But what we're trying to do is find something that's bigger than 8, which is 9. But there's no node here. So in this case, we would return false, which means that 9 is not in this tree. And that's essentially how to uh, sort of search in that binary tree. Okay. Now, I'm going to go back to what Pseudo Alibi said in the chat regarding balanced and unbalanced trees. So we'll go back to where we had it. So when we look at this balanced tree and we look at the unbalanced tree, obviously when we talked about the binary search tree, we know that binary search tree has a search of log n time complexity. So we know that it has a search of O log n time complexity, which means that it's not going to take n steps to search the whole thing, and well, not to search the whole thing. It won't take n steps to search for a target. And we've proved that here because obviously it only took us 2 steps to check that, or a total of 3 steps technically, because obviously when we talk about the binary search, we look at the root node, we look at this node and that node as well. Okay. Whereas here on this unbalanced tree, we have 3 nodes only. And you can firstly obviously see that this root node, it doesn't have anything else on this side. So we know it's unbalanced, firstly, because it's not sort of, it doesn't have the same amount of nodes on each side. So that's the first thing. And then also, when we do the search for, let's say we're searching for 3, because obviously it's technically in the same position as this balanced tree. We check 1, 1's not 3, it's less than 3, so we move to the right. 2, 2 is less than 3, it's not 3 either, so we move to the right again, and then we found 3. But that took us 3 iterations. But the size of the tree, which is just the number of nodes in the tree, the size of the tree is 3 itself. So we did 3 iterations on a tree of size 3 to find it, which is actually O of n, which is the worst case of the binary search trees that we were talking about. And when we look at balanced versus unbalanced trees, I think Hux was saying before as well, the more unbalanced you get, the less likely it is for a search to be log of n, which is, yeah, that's it, right? Which is why AVL trees matter as well. And just to quickly talk about that as well, AVL trees are just trees in which we have an always balanced tree, and it's also a binary search tree as well. So obviously we're not going to be covering that today, but it is something that is really important, and we'll be covering that next week, I think. So stay tuned for that. Okay. Now we've covered the basic sort of idea of a binary search tree. We've talked about balancing, or the balanced and unbalanced sort of trees and their time complexities for searching. And what I'm gonna talk about now is the insert and delete operations of the binary search tree. So let's have a look. We'll copy paste this again. So now when it comes to insertion, we need to make sure that we're inserting at the right place, right? So let's say we want to insert, let's say we want to insert 9. So that means we're gonna run this function, tree.insert 9, for example. That's just like some random command that we can come up with. Um, so to do this, we look at the root node and we go down until we find a space where a root node can be searched for. And this means that it will be in the right place. So, for example, we look at 5, we compare it to 9, 9 is bigger, so we move to the right. We look at 7, compare it to 9, 9 is bigger, we move to the right. We look at 8, 8 is bigger. I mean, sorry, no, 8 isn't bigger. We look at 8, we compare it to 9, 9 is bigger, so we move to the right. There's nothing here. Because we know there's nothing here, we can insert it. Because we know that this place would mean that it's going to be bigger than 8, and we know that 9 is bigger than 8, and that there is no node here, so we can add this. That's how we insert. So we compare the values as we go down in the tree and look for something where there is a space, which means that the node doesn't exist there. Okay, that makes sense. We're just going to be inserting 2 as well, just to go over that again. So let's start. So we want to insert 2. We look at 5. 2 is less than 5. We move to the left this time because 2 is less. We look at 3. We look at 2. 2 is less. We move to the left. Cool, thanks. That's good. It's good that's making sense. So we want, obviously we move to the left. We look at 1 and we compare it to 2. Here 2 is bigger, so we move to the right. There's nothing in the right, hence we can insert. And that's how we insert there as well. Now, when it comes to deletion, or the deleting of a node, there's 2 things we need to know. I'm just going to remove these because obviously they're part of the example. Let's say we're trying to remove 8. Now, firstly, we need to know if 8 actually exists. Because if 8 doesn't exist in the tree, why did we call the delete for? Oh, is my screen frozen? Do this, can you see it? You see that squiggly line on the screen? Oh, is it frozen for anyone else? Oh, hmm. Yeah, I'm gonna restart the screen share, so seconds. So don't know what's happened there, but I'm just gonna go back and share my screen again. Can everyone see my screen? And can you see this now as well? You should be able to. Yeah, cool. Awesome. Nice. So back to deletions then. Um, so when we're deleting from a binary search tree, firstly we need to make sure that exists. So if I run delete 9, tree.delete 9, obviously 9's not here. So obviously we don't know, well, obviously when we're at the root node, we don't know that 9 is in the tree. So when we traverse down to here, because obviously 8 is smaller than 9, and when we look there, if it's small, um, we don't need to return anything. We can just say, oh, there's an error, because there's no 9 in the tree. Okay, so that's the first case. Second case, we need to make sure that our deletion does not affect anything either. So, for example, I'm going to be deleting 8 now. So we have 5. So essentially we're just going to search for 8 again, because obviously from the root node, we don't know in the computer, obviously, that 8 exists. So we look at 5. 5 is less than 8, move over here. 7 is less than 8, move over here to the right. And we look at 8, we found 8, so we can delete it. Now, there's nothing below 8, there's nothing here. So that's good, which means that we don't need to do anything in order to keep the tree balanced, because the tree will always be balanced if we delete 8 anyway. So we can just delete it. And tree's still there, everything's still intact. And also, there's no sort of differences, which is good. Obviously, want to get this back. Now we're going to be talking about tree.delete 7. So we're deleting this in here. So let's do that whole thing again. 5 is less than 7. We move over here. 7 is 7. So we found 7. And we want to delete this. Now we look below. We actually have 2 nodes. We have 2 nodes here. So we need to know how we're actually going to delete the tree or the node here. Because if we delete this, obviously, where is this connected? No. So we need to find a way in order to delete such that we can keep the tree intact, right? So the way we do this is when we delete, firstly we check if there is a right node. So I'll just write that down. We check if the left or the right or both exist. Okay, and these are 3 different scenarios, which I'll be covering in detail as well. We'll talk about both first. So we look at 7, we found 7, and we know we want to delete this. Is there anything below us? Yeah. We have 6 below us, we have 8 below us. Now, obviously, we know that the right node is going to be bigger than the left node, because that's the way that the binary search tree works. So if I were to say, we've deleted this, but I move this up here, this is good, this will work. But we could also say, this works as well. And you might be wondering, if we can do both, wouldn't that introduce some sort of ambiguity? And that's a yes. So I'm going to expand this a bit further just to show what's going on. Because, for example, if I say, let's say this is 8, this is 7, this is 10, this is 11, no, sorry, this is 9, and this is 12. Okay, obviously this isn't balanced, but this is just for example. So let's say we wanted to delete 8. Let's say we just replace 7 with 8, right? So we do this. Now this is kind of unbalanced, right? Because obviously we've got a lot of stuff on here. We've got a lot of stuff on this side. So this 7 ends up being an unbalanced tree, which introduces an increase in the time complexity. So, for example, if we wanted to go down here, it would be longer, right? So what we can do instead is we look at the minimum value on the right hand side of the node. So I'll just show you. So yeah, it's 9. So in order to do that, what we do is we move to the right, and to find the minimum value, we just move all the way to the left, which is all the way that way, which is 9, as Ajiba said, which is good. So we look at 9. Now we want to swap that over. So we do this, get that. We deleted 8, we put 9 in here. And now you can see that we've improved the sort of time complexity for one of the lower leaf nodes. So essentially we've removed stuff that's on the bottom instead of keeping it there, which is better because we don't have to do as many iterations to get to the bottom. Instead, before when it took, for example here, before when it took us 1, 2, 3 iterations, and that takes us only 1 iteration to check if 9 exists, which is better. So that's the preferred method of deletion because it will help to reduce anything that's on the bottom. And to do that, like I said, we look at the minimum of the right node. And that's if we have both. So we replace the deleted with the minimum value of the right node. Okay. Now, let's say we were deleting 7 again in this tree, but we only had 1 right node. Now, that makes it quite easy because all we need to do is there's nothing here, there's nothing here either. So we can just say 8 and we're done. Simple. And same for the left. If I was to delete 7 again, we can just move up there and we're done. Hopefully that's making sense. Just let me know if you have any questions, or just let me know as well if it is making sense, obviously. And I'll write that down as well. Yeah, makes sense. Awesome. I'm just gonna write this down. Left or right? It will replace the deleted verb. Also, can everyone read my handwriting as well? I should have asked that before, but yeah, okay, cool. Because imagine I was just writing and I couldn't read it, that would be Very bad, but that's good. Awesome. Okay. So we've covered insert, we've covered delete, we've covered searches as well. And those are the three main operations that you need to know. What I'm going to be doing is I'm going to talk about quad trees now. But once we talk about quad trees, we are going to be doing a code implementation in Java of a binary search tree, and we'll see how it works in actual code. And okay. And also, it has been an hour. Does anyone want a break, or are we okay to move on? Just let me know in the chat. I have just been yapping for the whole hour, so moving on. Okay, let's keep rolling. Keep rolling then. Okay, quad trees. Now, quad trees, as the name implies, we have four maximum children in this tree. And you might be wondering, is it just the same as a binary tree? Well, no, it's got a little bit of a difference. So I'll show you what a quad tree is by just drawing out an example. Just drawing out this quad tree over here. And if this looks a bit confusing, I will explain the terminology as well. So don't worry. Just finally do this. Okay, cool. So this is what a visual implementation of a quad tree would look like. And you might be wondering, what the hell is going on? So I'll explain. So this box of four is a node. This node obviously contains the values and pointers to the values. This circle over here is a pointer, and it has this line that points to whatever we want to. What's the names of the what do you mean by the names of the pointers? So how you have three dots. Ah, okay, okay, cool, cool, cool. Yeah. Yeah, so like Hook's is saying, it doesn't really matter what the name of the pointer is. I could literally say um tree dot one, tree dot two, tree dot three, tree dot four. Literally, I could just say whatever. Um Obviously in coding, um we can have well, it's better for us to have a semantic meaning for the pointer. And what I'll do is, obviously, I've talked about this over here, but I'll talk about the actual, once I visualize it in a separate way, I'm just going to talk about it with respect to different names as well. So I'll just get onto that in a bit. So I'll just delete this for now. Okay. So like I said, we have the pointer. The line points to whatever we're trying to look at. For example, here we're looking at a value. So this pointer will point to 0 in memory, because obviously remember, pointers will point to something in memory in a computer. So this will point to 0, that will point to 10, that will point to 20. And then we have this pointer that points to another node. So for example, we have this whole node again. We have some pointers to some values. And then here, what I've done is I've just written random quad tree pointer, because it's just some random quad tree pointer. We don't care. This is just an example, obviously. Okay, now that's essentially what quad trees are. They are trees. I write it down. Quad tree is a tree that can have maximum of 4 children, and now obviously what you can see is that I've put them in order, but this quad tree, it doesn't need to be ordered. Like we were saying before, binary trees don't need to be ordered. Binary search trees need to be ordered because of their property in which we search in. So they have to be sorted. But obviously, binary trees themselves and quad trees themselves don't need to be sorted. I've just put them as such just so it's easier to talk about. Okay, so that's what the definition of a quad tree is. And what I'm going to be doing is I'm actually going to draw out a different implementation of a quad tree. I'm just going to visualize it in a bit of a different way. And hopefully this will make sense as well. Okay, 0, 10, 20. And this is actually something that Alan was on about as well, this sort of different way of writing it out. We have the random tree. How about that? And we have this tree visualized again, and you might be wondering what the hell's going on, because I've just written the values here in such a weird way, and you might be thinking, what is this guy doing? But I'll explain. So we have 0, 10, 20, and then this block, if I put it here, that block is a pointer to the next quad tree. So essentially, I'm just visualizing this from there. So what we're just doing is I've just made this whole thing into a square. I've put the pointers for each, and I've made it so that the pointer will actually contain the value itself. So this is a pointer, and it's also, so this whole square is a pointer to 0, like we've seen over here. And this is corresponding to that one. This one corresponds to that one. And then this corresponds to this new node. Okay. And obviously, like we have over here, this random quad tree pointer is over here. 50 is over here. 40 is over here. 30 is over here. And the reason why I've done it like this is just to show you, because obviously they're going to be ordered, right? So we have the first pointer, second pointer, third pointer, fourth pointer, and you can see that it goes in a clockwise direction. And that's how we lay this out visually. We'll just write it in a clockwise direction. And we've done that here as well. We start from 30 here, 40 and 50. Clockwise direction, remember? Okay. But I'll carry on, obviously. I'm not going to expand it any further because obviously I'd have to zoom in so much. But you get what I mean, hopefully. Um, does that make sense? I'm just going to go over one of the examples in the data structures and algorithms. How funny. So I'm going to quickly bring that up. Just bear with me. If you can't see what I'm doing, don't worry, I'm not frozen again. I'm just doing it on my computer. I'll share my screen as well on my computer. And actually, just before that, I'll just quickly touch on what Manjeev was asking in terms of the names of the pointers. Um, so the way that we've done this is so that we can have names for these pointers. So here we have the top left, we have the top right, we have the bottom left, and I mean, sorry, the bottom right and the bottom left. And that can be used for a name for the pointer. And that's what Alan's done in his data structures and algorithms PowerPoints as well. Okay. Then now what I'm going to do is I'm going to share my screen. So node.bl will return the whole root node for that with the rest of the tree below it. Kind of, yeah. So what node.bl would do is it would return the reference in memory to that pointer. So this over here. And yeah, so essentially you could access all the random Q trees that we've had in there as well. Awesome. So I'm just gonna share my screen now on my other account. So just bear with me for a second. Actually, to be fair, I could write it down here. So I'll just write it in fact. Probably is good as well for that. Write it down. Sit in silence for a bit, I guess, whilst I'm writing this down. See, make Q2 and change button. Q2. Probably what same one or books. Again and again. Up here because of brackets. Okay, and this one as well, obviously. Okay, cool. So now what we're looking at is we are looking at a rotation of this pottery. Um, might be wondering what the hell's going on, because obviously we've got all these different recursive calls to the function rotate. So essentially what we do is, firstly, we're checking if it's a value and not a pointer. So obviously we're checking if this is a value, or that's a value, or if this is a value. This is a value, obviously. This isn't a value, this is a pointer. This whole block right here, that is a pointer to a different node. So if it is a value, we return the quad tree, which is great. However, if it's not a value, then we return the make quad tree function, and we rotate. Oh, sorry, I'm actually by bottom left, top right, and bottom. Sorry, wait. Top left, bottom left, bottom right. So that's just to make it a bit easier. I'll just copy from the PowerPoint. But yeah. So here we return the bottom right, the bottom left, top right, top left. And this will be a recursive call which will return the value. Because obviously we're looking at the value here. It will return a value up until the point where we have a new quad tree. So we'll do this algorithm. We'll just do a dry run of the algorithm on paper. Well, not on paper, but on my Samsung tablet. And I'll just show you what happens. Okay. Oh, 1, 2, 3, and 4. I'm not going to contain any pointers just because it complicates things a little. I'm just going to go for a simple dry run of the algorithm. Uh, we start off by having a look at the pointer to the quad tree itself. That whole massive pointer, the square. Now, if it's a value, well, it's not a value. So we go to the else, and then we return, make quad tree, rotate this, rotate that, rotate that, rotate that. So essentially what this does is it just makes a new quad tree. So let's see what actually happens. So we rotate bottom right. Oh, sorry. So bottom right, I'll just label these as well. Bottom right, top right, top left, bottom left. Okay. So we look at this first bit, rotate bottom right in the quad tree. So we look at the bottom right, that's this, right? So we've looked at this, and we're here now in memory in the rotate function. Now, when we do rotate is value quad tree, so we check if this whole thing right here is a value, we return it. And it is actually a value. So we return it. So we return 3. So instead of having this now, it's 3. And I'm just going to get this all out just to show you the iteration of what's actually happening. So instead of what we had above, it's now 3. And when we do the make quad tree function, by the way, I should have said before, it will make the quad tree like this. So we have value 1, 2, 3, and 4, where this is the first value, second value, third value, and fourth value. Does that make sense, guys? Just pop a yes in the chat if it does, and no if it doesn't. Wait, can you guys hear me as well? Yeah, okay, cool. Awesome. And am I delayed or is it still, are we still chilling? Perfect, nice. Okay, so we'll just get rid of that. And we now um I've written a BST implementation for other separately. Nice. I'll go through the delete as well after this actually. So we can have a look as well at that if you want. Okay, so go back to the quad tree. So obviously we've done this part. We're done because we've returned it. And we returned it here. So that will return 3 here. Then we go down and we look at the rotate of the bottom left of the quad tree. Now, quite similarly to what we did before, we look at the bottom left and we check if it's a value. And it is. 4 is a value. So we return 4. So now that's that. We look at the top right. We look at the top right. Is it a value? Yes. So we return. We return 2. And this will be here. We look at the top left. Is it a value? Yes. We return the quad tree. And the quad tree is the value, so we return the top left, which is 1. So we've now done everything. We've looked at the recursive implementation of this what do we call it? Of this quad tree. And now when we return this make quad tree, this will make a quad tree such that we have something like this. 3, 4, 2, 1. And if we compare this to this one over here, we have the result and we have the original. You can see that we've just rotated it and we've rotated it this way by 90 degrees. So we've rotated it clockwise. I mean, not sorry, 90 degrees, sorry. 180 degrees. And we get this. Because obviously what we do is we put this here, we put 2 here, we put 3 here, and we put 4 here, and then that's 90 degrees. And then what we do is 4 here, 1 here, 2 here, 3 here. And that's what the rotate function does. That's just a sort of dry run through our algorithm, which is the rotate algorithm. And that's just to sort of demonstrate how recursion works our in our project. Okay. Does anyone have any questions? Doing let them know. Awesome. Cool. Good. All right then. So we've covered quad trees. We've covered how to rotate quad tree. We've covered binary search trees, the operations or the basic operations of a binary search tree. Now, finally, we are going to jump into the code of how to code a binary tree. And It has been 1.5 hours. So does anyone want a break, or are you okay to continue? About me. Short break. Okay. My recording is still recording somehow. Yeah, I don't know why. But it's still recording, which is good. So yeah, what I'll do is let's do that. Um, we will have a look. We'll have a 10-minute break. We're not gonna have like a 2-minute break. Um, and what we'll do is we will cover the code in the next section. And yeah.